First of all, thanks for the invitation. George not here, but was his idea. So this is a talk is going to be similar to the one I gave at CMU Carnegie Mellon database group recently last year. I will just go deeper on one particular aspect, which is cardinality estimations, which is the area where I personally feel there is most innovation happening at Stardog. So as Nikolai said, I'm the tech lead on the query engine group. So I'm basically responsible for the query optimization and execution at Stardog. So I'll have to tell you briefly what Stardog is. And then I thought I would have to introduce RDF and SPARQL because that's what I normally have to do. But now looking at the list of participants, I'm just thinking maybe I'll skip that altogether, or maybe I'll just spend a couple of minutes. And then we'll go straight into the Stardog query optimizer. I will not go beyond something which is called BGP-based graph patterns. In SPARQL, that will be unnecessary for the cardinality estimation talk. And then we'll spend most of the talk talking about just statistics and cardinality estimations. In particular, I want to discuss how we use one specific data structure called count-min sketch. So Stardog as a company, it's a US company which has been around since 2006. And we did some consulting in the semantic tech area initially, but then started Stardog as a product in 2010. And now it's version 8, and version 9 is going to be released a couple of weeks. So we usually work with, like, we don't have lots of smaller customers, like we don't have thousands of people using Stardog. We sell to fewer larger customers, most of which are large enterprise companies. And we do that because they usually have the data integration problem, multiple databases, they want to run queries over all of them, and this is where Stardog sits as a product. I myself has been at Stardog pretty much after I finished my Ph.D. in 2011. I did a short academic break, 2012 to 2015 at the University of Ulm, working on something else on logical reasoning. And so basically my job is to make sure that Stardog queries run fast, or at least fast enough for the use cases. And when users cannot make a particular query run sufficiently fast, they report it, and one way or another it comes to my group, to me usually. So I've been looking at all those queries which have been slow for various reasons over many years, and this is basically what informs the optimization work which we're doing. Okay, so what is Stardog as a product now? So if you go to the website and start reading the marketing stuff in there, you're not going to have the impression that it's a database. You're going to read something like knowledge graph, data fabric, enterprise data integration. But if you unwrap all that stuff, somewhere in the middle, you will find the graph database with this storage model, storage backend, query engine, and that's what I work on. So as a database system, it has pretty familiar set of components. It has a storage engine based on RocksDB these days, which is key value store, write optimized LSM trees. That was since Stardog 7. Before that, it was a homegrown storage layer, which was optimized for a different set of use cases. The graph data model is RDF, but as I will try to emphasize, like the specific syntax which we use, like RDF or property graph, is less relevant to what I'm going to explain today. The query language and update language is SPARQL, which again, for most of the purposes, is just a graph query language. The system has some pretty rigorous transactional semantics, which is not common for graph databases. It's more common for SQL databases. So we support full ACID. We handle concurrency control using MVCC. So transactions run in parallel. and transactions are isolated under the snapshot isolation semantics. We have both single node and cluster deployments. What's important there is the cluster is not for horizontal scalability, it's a high availability cluster. So it's a redundancy-based cluster, which works under this strong consistency model. So no eventual consistency stuff. And it has some built-in data integration virtualization solutions, which is the biggest selling point for Stardog right now, but I will ignore it completely today. Mentioned the implementation, it's a hybrid Java C++ kind of system. The storage engine, which is RocksDB, written in C++. There's a layer on top of that, which is also written in C++, which handles data updates. But the query engine, the optimizer, and the execution, that's written in Java, and that's what my team is responsible for. Okay, so briefly what RDF is, just in case someone on the call doesn't know. It's basically just a graph data language with some web-friendly syntax. Like your data is represented, many nodes is represented as IRIs. And then there is some logic and model theory to define the semantics of the language, like what it means, for example, to say that two graphs are equivalent, or what it means for one graph to entail the other graphs. And lots of papers have been written about that. There's a lot of complexity in there, but it's totally irrelevant for most of the implementation effort, actually. So if you just want to implement the SPARQL query engine, a lot of that model theory of RDF is less relevant. So just a simple example here to illustrate the point that RDF is just a graph. So you have information here that John knows Mary. That's one edge. John is called the subject of that edge, or triple. Knows is the predicate, and Mary is the object. And John likes beer. John has age, which is a number, not an IRI. And Mary works at Google, and you can visualize it as a graph on the right-hand side. So it's you can use another graph model. You can use property graphs to express the same thing. So there's nothing really special about RDF there. How you store that in the database is, of course, a completely different story. You can think of it as a single large table with 3 columns. Typically not how it's implemented these days, but conceptually, it's just one large table with 3 columns. So SPARQL is a query language. Again, there is a lot of in the spec, in the SPARQL spec, and there's a lot of features, there's a lot of expressive power in the language. But at the core, it's basically the first order conjunctive query language over RDF data. Plus, there's some extra features. There is support for recursion. There is support for outer joins. There is support for negation. There is all other stuff. But today, what's going to be important for us is that it's the first order conjunctive queries. So the query you have on the screen is taken from one of the older SPARQL benchmarks called SP2B. It's a publication data benchmark. So it asks for names of people who authored at least one journal publication, like one article, the first 2 triple patterns, and at least one proceedings paper. So we have articles written by people, we have proceedings papers written by people. If those 2 things are written by the same person, I want to know the name of that person. So you can write the same query as a data log in a data log syntax, for example, because it's just the first order conjunctive query. So SPARQL has pretty well written spec, and it's a declarative query language. And the semantics of every SPARQL query is well defined by something called SPARQL algebra. So for every query in a particular data set, the result of the query is well defined. Well, there are some gaps in the spec. The spec is not perfect, but at least in the majority of cases, the answer to every query is well defined. And it's defined by algebra. So for every query, there is a canonical way how the query should be parsed and represented as an algebraic expression. which is very similar to SQL. And SPARQL does actually have a lot in common with SQL, and the implementations of SPARQL also have a lot in common with SQL, and that will be important today. So for this particular query, if we look at that expression, we'll see that, okay, there are familiar relational operators. So there's the distinct, there's projection, two variables, and then there's a basic graph pattern in the middle, which is the key part of the query. So what this BGP is the next question. And by the way, if you have any questions while I talk, just feel free to interrupt me. Like I don't see the chat for some reason. Like I don't know, something is wrong with my layout on the screen. So if you just type it in the chat, I'm not going to see it. So you can just interrupt me and ask a question. That's fine.
All right, we will.
Yeah, it makes it less boring. Okay, so let's spend maybe a minute just to make sure we're all on the same page how BGP execution is defined. So you see this query, just the BGP part of it, like no projection, distinct stuff. And the BGP matching is defined by subgraph homomorphism, which is a scary word for engineers. Like I guess in this community in academia, you all know perfectly what subgraph homomorphism is. Usually when I talk to software developers, I need to explain that part. So what helps is you just think of the BGP pattern as a little graph with blue at the top right. And then you have your data graph in black at the bottom. And basically, you just look for mappings, like how you can embed that query graph into your data graph. So for example, if we start with two triple patterns, the article, so the node which has two outgoing edges, the type edge and the creator edge, you'll see there is one match here. And then we have another match for the proceedings paper. So that's node Y. It also has a type edge and the creator edge. And they even they join on that node, John. So John has authored both. And then for the last pattern, the John has a name. So now this is a mapping from the query graph to the data graph, one particular subgraph. And then, of course, it works same way for the other subgraph. So Mary is another result for the query. So that's how it's defined. How it's implemented is, of course, completely different story. The spec is not going to tell you that you need to traverse the graph, you need to do joins, so you need to do something else. As long as the results are the same, your query engine is doing the right thing. Okay, so now let's talk how this works in Stardog. So I always I put the slide in there, this slide has been here forever, and I just realized at some point I need to change it because usually at this point there's someone in the audience who just says that, well, if you translate every triple pattern into an index can and then just start joining all those index patterns, then you just have too many joins and it's not going to scale for a bunch of different reasons. And those arguments are valid, I think, but there's a lot of nuance here, which I physically cannot explain on this one slide only. So I would still prefer today to work in this simplified model in which, yes, every triple pattern, like 5 here, is an index can, and then we join them all together. In reality, of course, there are aggressive query decomposition techniques which group some scans together before the general join order optimization phase, and then some of them, and we have n-ary joins, so we don't use just binary joins, but none of that will be hugely important for the key parts of the talk. So let's just assume for now that we have huge number of joins. Okay, so that's one way to implement BGP. Not the only way, but the one we've been using at Stardog. And now the question is, of course, well, so this query has one triple pattern, which probably not going to return a lot of results. So the creator of the paper should work at Stardog, and Stardog employees are engineers and academics. So we have published some papers, but not many. So we probably should start there to execute this query in reasonable time. Why? Because it's so-called selective criteria. But how do we know that? In general, the join order optimization problem, like in which order we execute all those joins, that's one of the central optimization problems for databases with relational query languages with join operators. It's totally possible to get the join order right, but still have the query running slow because something else is wrong. But if you get the join order wrong, there's probably nothing else you can do to save that query. It's going to be a slow query in most cases. So that is not the only thing you need to get right, but this is definitely one of those things you have to get right if the query if the query is complex and data is large and you need to run fast. It's an optimization problem. It's an optimization problem for databases which use the so-called cost-based optimizer. And the idea of cost-based optimization is that every join order, and by the way, I should say, like, it should be obvious, but I should say it explicitly, that all the different join orders, they're going to return the same results for the query, basically for the same reason that you can rearrange arguments of a multiplication operation in algebra and still get the same results. So they're all going to return the same results, but the runtime will be
Pavel, can I make a remark?
Sure. Yes.
The market is going to come from me. You may have anticipated this, but I mean, you say, and you're right, that in the join order problem and cost-based optimization, it's kind of really the same between RDF and SQL or relational systems, and that's I'm in agreement. However, in SQL, this particular query would have 0 joins. Okay.
Right.
Because you're basically scanning the kind of article table, you could say, and you're doing a selection on those that have an author, but the author affiliation is well, you basically check is Stardog, so you basically yeah, that would actually be a filter query, and what is a bit. So the problem, I mean, I actually gave some talks and I make these claims, but now that I have somebody from the RDF industry, I cannot stop not saying this, is that, considering every single property at join, while in the data, you will see that for articles, you will always have a creator and you will always have a title, and you will always have an in proceedings, at least for academic papers. So it's like these are all one-to-one joins, and they are heavily correlated. And you can actually, if you would look at the structure of your triples, you would actually discover that you will find that they always co-occur. And you could therefore store them. I mean, an intelligent kind of storage system could actually pick up on that and actually group them. And then you would have, in this particular case, 0 joins or maybe 1 join. And the problem with the join ordering problem is it's difficult to solve because it's exponential in the search space is exponential in the amount of joins. So it's like having more joins is a big thing. It's like it's exploding, and the search space is going to be explored less well on very large joins just by necessity. So, I mean, while I'm not taking away anything of what you're probably going to tell about how to smartly pick correct join orders, this is also something that could be very helpful for your users.
No, I'm familiar with that line of arguments, and I agree. Yes, so there was actually a system which did something very similar to what you're describing. So the IBM DB2 extension for RDF so what they did essentially said, okay, we like all the data for articles and proceedings is going to be queried together, so let's just store in one table instead of doing joins. Right? So instead of like, and I'll mention that later. And that definitely does help. So it makes the query optimizer life much easier because the search space is much smaller. It makes the execution engine life a lot easier because you don't have the joins, and it improves the locality of scanning the data massively. But then you also cannot ignore problems which are going to happen when when you start changing the structure of your data, like dynamically, if your storage is tuned to one particular model of your data, which you either have explicitly in the schema or you infer it somehow during the query execution. So, and I believe that project eventually failed, not necessarily for that reason, but for perhaps a bunch of other different reasons. And we looked into that as well. And so I would say that maybe 5, 7, 8 years ago, it would have been much easier to go for that storage model because the RDF data sets were mostly static. It was more like Wikidata DBpedia use case. You like once in a month you publish a new new release, you load the data, you optimize the storage, you precompute a bunch of statistics, you precompute a bunch of indices, you do tons of work, and then you run queries fast. And then next month you wipe that data, load again, optimize, query. And that was actually our life at Stardog when we started till pretty much like 2017. We could assume that the read performance is way more important than the write performance. And unfortunately, at some point, we couldn't really live under those restrictions anymore. And these days, we don't even I don't even call Stardog an analytical database anymore because the transactional use case is getting more and more important. People want to modify graphs more and more, and they want flexible scheme. They don't want to rigid constraints like, oh, you want a new predicate, you need to add like a new column to the table. So that's it's still possible, but it's not really universal recipe for solving all these problems, I feel.
Yeah, you're right. You're right that then becomes a problem how to maintain this discovered structure. But it would be interesting to actually
yeah. Well, actually, I'm gonna talk a bit more about this. So let's just bear with me.
I'll just don't feel held up by me. Just
okay. So let's just go back to the what Peter just said about how huge this search space for joins actually is. So you said exponential, it's actually worse than exponential. It's more like factorial because basically every permutation of your operators is a valid join tree. But even worse than that, on top of that, you also have like a choice of join algorithm for every intermediate node. So you can have hash joins. Every mature system has a toolbox of join algorithms, including Stardog. So we have merge joins, hash joins, different variations of hash joins, we have bind joins, we have loop joins, and so that makes the search space bigger and bigger. So for example, in this example, if you want to find articles written by Stardog employees, on the left-hand side, there's a hash join at the top, which would put all Stardog employees to the hash table and then iterate over all articles written by anyone in the world, which is not a great query plan. On the other, on the right-hand side, the query plan would first get all articles written by someone in Stardog, sort that's a small subset, and then do the merge join with the collection of articles, and that will probably complete in milliseconds. Okay, so just to recap, the reasons why the join orders could be bad, like I've seen 3 big reasons. Like I see daily 3 big reasons. So the first is the failure to explore the some parts of the search space, because as we said, it's a huge search space. Second is an incorrect cost model. So in that case arises when you have one query plan and then another query plan A, query plan B. Query plan A is more expensive than query plan B according to the cost model, but runs faster. So that just means your cost model is bad. And then the number 3 is the bad input to the cost model. And the input is cardinality estimation. So the case number 1 is kind of inevitable because you can never explore the search space.
Sorry, Pavel, to bring in a 4th point, but it's related to my interruption before. That is correlations, because some of these joins, because they are not real joins in my view, or my definition, kind of they move together because there is this kind of one-to-one relation between, for instance, an article and ISBN number, because cars don't have ISBN numbers, but articles always have an ISBN number. So you have these joint correlations, and that makes it actually hard. That makes it even harder because very many times the independence assumption is used for combining estimates. But these things are not independent; they behave in a correlated way, and this further distorts the cardinality estimates. That further distort the search for a good query plan.
This is exactly what I'm going to talk in just a minute. Just if you let me go through, I will get to exactly that point, because the rest of the talk, if I have time, we will talk about correlations and how to figure them out later. But yes, I totally agree that that joins, if you can get rid of joins and store the data such that the joins will not be needed, then you don't have to listen to what I'm going to say if you solve the problem on that level.
Not entirely, because also in our SQL databases, we sometimes have correlated joins. So keep on going.
All right. So, okay. So reason number one is kind of inevitable, but surprisingly rare. So we do see the cases sometimes when the join order optimizer stopped before it could get the best query plan, which it would have gotten if it was allowed to go for it a little bit longer. But it's rarely the case that the query plan is then disastrous, or query timeout or something. Usually you get a reasonable query plan in the, at least as far as joins are concerned. So the reason number two, incorrect cost model, that happens every once in a while, because cost model is complex function. You cannot abstract away everything. Like you cannot really take into account everything. Like you don't know, for example, if some other query comes in the middle of your query and starts consuming the resources. But that's usually, like if you have a really bad case, it's usually possible to tune the cost model. And over the years, we've been tuned our cost model pretty well, I think. So case number two is not really a problem. But case number three is the reason I'm here today, because the cardinality estimations could be way off, and the main reason for that is exactly correlations, which the query engine has no idea about, and that's what we will talk about. All right, so the basic question is, you have a BGP, and maybe the results of that BGP is going to be joined with something else in the query, and the query optimizer has a question: how many results will this produce, or is likely to produce? Like it wants a crystal ball, such that it would look in there, and the crystal ball will say, oh, this will probably produce somewhere like between 1,000 and 10,000 results. So the easiest way to estimate cardinality is actually to run a query. So that's I never mentioned that during my talks, but someone actually asked me, like, why don't you just run a query and get your estimate 100% correct 100% of the time? And I said, okay, so maybe we should spend some time talking like why this is not possible. And the main reason why it's not possible is because the query optimizer requires a lot of estimations for a lot of different combinations of join during the optimization because of the search space. So those estimations need to be very, very, very fast. Like you cannot touch the disk or network. You basically can do lookups. So it seems obvious that if you cannot go to the data for statistic, you need to precompute it and keep it in memory. But then you're going to run into troubles because the query engine does not know the schema, because there is no explicit schema like in a relational system. There's usually an implicit schema, but not explicit. The query workload may not be known in advance. If it is known in advance, then of course you can always estimate patterns which occur often in queries. And the data can be large and change fast. Unfortunately, so the last bullet is especially unfortunate, the fast change in data. That's a relatively recent phenomenon, in RDF at least. So what can we reasonably precompute under these conditions? So now I'm gonna say what we precompute at Stardog, because it's always a trade-off between like how much you precompute and how much time and computational resources you spend for that. Because every time you decide to precompute more, your loading becomes slower, your updates become slower, or something else suffers because you have to spend resources. So it's a trade-off, and a trade-off which you need to take to choose very, very carefully. And the number one thing which we precompute is the common star-shaped graph patterns. So for example, this PGP on the screen, it's all about article. Okay, so before Peter mentions that, yes, this could be a table, so not a collection of joins. But this is actually interesting, like, and I will go back to why it's important that it could be a table. But first, I want to say, like, why star-shaped graph patterns are common in queries. Because in every SPARQL query, you will see, most SPARQL queries, you will find something like this. It's because it's a common way to model business objects as graphs. And also, it's a direct reflection of tables. And most graph data sets, they have been tables at some point, like many of them. So, for example, this could have come from a publication table with columns like type, creator, published in the volume, which now became edges in the graph. So if we could precompute the number of results that this pattern matches, that's a pretty big help. Now, the question is, of course, how many of those distinct star-shaped, like how many distinct collections of predicates you're going to precompute? Because, you know, we're talking about subsets, so it's a 2 to the power of number of predicates in the data, which sounds like a pretty, you know, computationally intensive problem, but it's surprisingly easy and cheap. And the reason for that is that the number of distinct star-shaped patterns in very large graph databases is surprisingly low. It's like in hundreds, like up to 1,000, rarely above 1,000. If you look in something like Wikidata, that's going to be an outlier because it uses a lot of data from different sources. But in enterprise data sets, it's usually like hundreds. Why? Because they have been tables at some point. And like, how many tables are going to have in your relational schema? Could go above 1,000, but there are way more databases where it doesn't. And we can figure that out while in one pass over the data in a streaming fashion, like while the data is being loaded. So that's not our idea. The idea goes back to Thomas Neumann, his famous characteristic sets paper for the system called RDF3X, 10, 12 years ago, maybe. And so he suggested that it works brilliantly. But you start using it, you start running into troubles pretty quickly. And the first difficulty is, okay, what happens if the query doesn't just have a star-shaped pattern, but there is a constant. So we are not just interested in all objects with type edge and creator edge. We are interested in articles. So Neumann, of course, was aware of that problem. So he said, basically, okay, precomputing correlations between objects and every object and every characteristic set seems, you know, intractable. But let's just assume independence between the article and this particular collection of predicates, which basically is like saying if 10% of objects in your database are articles, and you have 100 objects with type and creator links, then we will assume that 10 of those are related to articles. And this is a standard independence assumption. It's a standard assumption in statistics. If you cannot precompute something, you assume independence. It's like your null hypothesis, like the least, like the most neutral assumption which you can have. And in many cases it works, but we can do better. And the most useful thing we do, I believe, is that we complement this characteristic set idea for star-shaped patterns with something called count mean sketch, which is absolutely beautiful data structure. I like it's the one which I can talk like hours and hours. It's really that great. So if you know what the Bloom filter is, probabilistic set, basically. So the count mean sketch is the same idea, but it's probabilistic multiset. So you have a stream of objects, the same object can occur multiple times. You run that stream through the sketch, and after that you ask how many times that object occurred in my stream, and it's going to say 5. maybe 7 or maybe 0. And the way it works is extremely simple. You have a few pairwise independent hash functions like h1, h2, h3, h4. You hash the object, so that maps it to different cells in a table, and then you increment the counter every time you see that object. And you run the stream through the sketch, and then when you have a query against the sketch, like how many times this object occurred, you hash it again, you look at those cells, and you take the minimal counter value over all of them. Like why minimal? Because of hash collisions, other objects could be hashed to the same cells, but it's rare that another object will be hashed to all of them again, because the functions are pairwise independent. So the estimation is pretty good, and the amount of memory is really small. All right, okay. So what sketches can do well, what it can not do very well? They can recognize very frequent objects in your data sets very well. So if you have an object which occurs like millions of times in your database, Sketch can know about that. There's with a very high accuracy. But there's, of course, inaccuracy. It will overestimate. It will never underestimate. And it cannot, it does not deal well with objects which do not occur very often. Like it cannot distinguish between objects which occur rarely, maybe a few times, and objects which do not occur at all. And that tends to be fine most of the time. But actually remember the statement of mine that it tends to be fine, because I'll come back to it later. So how do we add sketches to the characteristic sets or the star-shaped graphs? So the characteristic set has multiple predicates, like n in general. And in principle, each of those predicates has a range with a bunch of objects in there. But instead of attaching a sketch to each predicate and multiply it by the number of different patterns and spend tons of memory, we just use one sketch for each characteristic set. And the question is, why does that not create troubles? And it doesn't, in our experience. And the reason for that is, in most cases, in most real data set, at least in enterprise, the property domains are largely disjoint. For the same reason that in many tables in the relational scheme, the columns have disjoint ranges. And if that is true, then the sketch is going to capture the correlation between objects and characteristic sets pretty greatly. So, for example, if you look at the type assertion in your data, and only 1% of those are articles, but if you look at the objects which have creator edge, and 90% of those are articles, so that would be a correlation. That correlation we will recognize 100% of the time, very accurate. So that's for star-shaped graphs. Now, next bit, chain estimations. Another common thing in SPARQL queries. You see things like, so we're querying for the creators of articles, and those creators have names. So that's so in RDF, like in property graph, the name would probably be an attribute, but here it's a chain of 2 edges in the graph. And basically our question is how many instances of the create name chains occur in the data, and we can precompute that. And then we realize that, oh, it's actually it's a foreign key constraint, like exactly what you said, Peter, earlier. We can recognize that later because we see that the number of chains is equal to the number of edges for create, and the average out degree of a name is 1. So we understand, okay, it's functional property, and this chain is basically a foreign key constraint. So we're going to know about that as well. And again, surprisingly, there are not so many frequent chains in the graph. So many chains, but if you impose a threshold, then those which occur very many times, those are not many combinations. And it's not that difficult to precompute all of them. It's more expensive than star-shaped patterns, at least given the indexes which Stardog has, but it's still not a huge deal. And then similarly to star-shaped patterns, we attach a sketch to the right end of each chain. So if some constant occurs very many times at the end of the chain, like for example, Paul Erdős, lots of people authored papers with him. We're going to know about that at query time via some very cheap lookups.
Pavel, can you tell
Sure.
us why do you discard the low frequency chains?
Just because we cannot spend arbitrary memory on that.
So there's too many of them, and then don't store.
Even if you have memory, another problem is that your lookups needs to be very, very fast at the query optimization time. So it's both, it's the memory requirements, and then you need it to be really compact such that lookups are fast. So those two constraints do not really allow you require some bound on the number of chains which you can precompute.
I see. And you're keeping the high frequency just to avoid the bad plans, I guess, right?
Yeah. Well, okay. We want to know, we want to know that if some chain matches many results in the data, then, well, we might want to postpone that join later.
Okay. Yep.
All right. So the last thing, there are multiple other things, but the last important thing is the joins on the object variable. Again, same query. You see that the articles and the proceedings papers, they have the same creator. So it's another common thing in SPARQL queries. So in principle, we could treat that as a star-shaped graph, but instead of ages outgoing, they would be incoming. But that would be a bit of an overkill, we felt. And instead, we just treat these things as chains, but undirected. So so that the right link of the chain is inverted, and then we can precompute it. At least we can store it using the similar approach, and we can look up using similar techniques. So now let's just put this all together and see how this BGP is going to be estimated in Stardog. So that's the graph representation of the query. So the step number one, we turn the table and we create a different graph structures, something which is called the join graph. So now the nodes are not like variables, the nodes are patterns, and they are linked by an edge if they are in a join. So for example, the edge always has like a join condition, which is a common variable. So it's a quite useful representation of the query if you want to know this, if you want to estimate this selectivity of each join or the cardinality of each join. And now your job becomes to cover this join graph with the statistics that you have available. So we start looking at the query graph and say, okay, so there is a star-shaped star-shaped pattern. We do have statistics for that, the characteristic sets. So we cover that and cover that part of the join graph. So the next instance of the star-shaped pattern, same thing. We have statistics for that. We cover that as well. Now, what do we have left in the join graph? We have left the join on the object variable, and we have statistics for that as well, because and finally, one last join for the name, and we have chain statistics for that part. And after that, every node in the join graph is covered. We have something we called MST, the minimal spanning tree of the join graph. The selectivity of every edge is estimated. So now we can just basically do the simple math, multiply the cardinality of all nodes times the selectivity of all edges, and we'll get our result. Okay, but now I don't have much time left, so I'll try to get to the part which I'm really excited about, which is the sketch. So, so the estimation errors will always cause trouble. So there's no way around estimations being imperfect. And the nastiest thing about cardinality estimations is that they add up. So the small error at the bottom of the query plan is gonna, become larger and larger errors as you join more paths, as your query becomes more complex, and then it might easily become a couple orders of magnitude bigger, at which point join order optimizer starts making wrong choices. And so the small errors, which they can grow into bigger errors, and those small errors often come from sketches, unfortunately. So I told you before that the sketches not distinguish between object which occurs once and the object which occurs like 100 times. So maybe object does not occur at all. So it cannot distinguish between rare objects and non-existent. And I said it's fine, meaning that if you're like building a hash table, it usually doesn't matter if you're going to put like a single row into a hash table or 100 rows into a hash table. On modern hardware, it's nothing. It's going to be microseconds either way. But if those errors add up, then they become problems later, and also they can cause the instability. So, for example, you have a query in which there was a constant like John, and the estimation was maybe a little bit incorrect. And you had one query plan, then we changed that constant by a similar person like Mary. Since the sketch cannot really distinguish between those two objects, they're not Paul Erdős, right? They haven't published a huge number of papers. So the query can change the query plan, even though the change to the query itself is very small. So even if the query doesn't become much slower, maybe like twice slower, users absolutely hate that experience when they make a small change to the query and then all of a sudden there is a totally new query plan, a different runtime. So that's not great user experience. And it gets bad if sketches are sensitive to internal data encoding. It's an interesting topic, but I'm not going to have time for that. So the last thing which I want to show is the ongoing work. So the previously what I was talking, it's pretty much settled at Stardog. We believe like we know what works, what doesn't, relatively speaking. But here, this is something which we've been doing with my teammates recently, and this is where I think input feedback would be cool. So if you look at a single sketch, so you ran the stream of edges through the sketch, and you put a bunch of objects into the sketch. Usually, you see some kind of power law distribution of the frequency of those objects in the sketch. So you will see that most objects, like on the right, they don't occur very many times in the data stream, but some objects occur quite a lot of times. So that is not uncommon at all, which is actually pretty good news for the sketch. It's one of the reasons why sketch is so useful in those cases, because the more skewed your distribution is, the better the sketch is going to work. If your distribution is completely uniform, the sketch is useless. Like it's just like every object is random. I mean, you can just flip the coin, and that will be just as good as your sketch estimation. But for the skewed estimations, it's pretty good. So this is what I'm trying to illustrate here. To the left from the green dotted line, we have objects which occur very many times, and estimations for those are accurate. To the right from the orange line, we have lots of objects, but they all look kind of random, not similar to each other, occur a few times, and the estimations there are unstable and inaccurate. So the idea is we should be able to use the sketch only for those cases when it's accurate, and use and abandon it for the cases when it's not accurate. So that's a very simple idea. So use it in its sweet spot use case and not in other cases. But of course, like if you have an object, how do you know? Like if you pull an object from the sketch, how do you know if it's to the right from the orange line, or to the left from the green line. You don't know anything about that object. The only thing you know about it is what Sketch thinks its frequency is. So instead of the next idea is that let's look at what Sketch thinks the frequency is, and if it's above a certain value, we believe the Sketch, and if it's below the certain value, we think, okay, you probably don't know much about this object. Like you don't know really if it exists or it doesn't exist in a data stream because the estimate is low. So that's the idea. But then, of course, like every time you start talking about thresholds, the immediate question is, okay, how do you pick the threshold? Or what happens if you decide that you cannot use the Sketch because for a particular object because the estimation is going to be unreliable for that object? What do you use then? What's the plan B? And with statistics, by the way, you should always have plan B, because the plan A is not going to work 100% of the time. And the plan B in this case is something which we call fallback estimation. And again, the idea is extremely simple. Let's say you build a Sketch for all objects which appear in the range of the creator predicate. So you have the multi-set of all people who authored the paper. And then you have some people who authored many papers, and you have some people who authored maybe 1 or 2 or 10. So you query the Sketch for John, you get the answer which is below the threshold, and then you conclude that John is an average person in terms of its publication performance. Like it's not extraordinary, like it hasn't published thousands of papers. So let's just pretend that let's, instead of John, use a random constant see how many papers the average person authored. And that number we know because this is just an average in degree for the created predicate, which is easy to precompute. So that allows us to make sure that the estimations for all the people who authored only few papers are stable. They may not be super accurate, but they are stable. So the query plans will not change abruptly if you change from John to Mary. And we have those fallback estimations for every use case, like for every case where we use a Sketch, we have the plan B and the fallback estimation like that. Sometimes we fall back onto independence assumption. Sometimes we fall back into something else we precompute, but we always have that fallback.
Pavel,
yeah.
You know what would be very stable? Just return 42 for everything.
Yes. Well, actually, I mean, I've talked to customers who said basically, we would prefer this query to be 10 times slower, but always 10 times slower instead of very fast in 95% of the cases and very slow in 5% of the cases. So that is true story. Yeah, that is true story. Like we have to deal with it like every time we release Stardog, because we have customers who would, like, let's say their workload is 1,000 queries. We release new version of Stardog, like 950 queries get faster or don't change, and like a couple queries get slower. And this is a huge deal. Like you cannot even imagine how many complaints we get about that, because people don't look at average. They look at those cases which create troubles like here and now. So this is why stability is important. And it goes to the estimations for, you know, and it's directly linked to the stability of your estimation. Sometimes we have to trade accuracy for stability, which is exactly what my last slide, my last 2 slides are about. Like what happens if you start like we still don't know very well where that threshold should be. Like if you make it too high, what does it mean? If you make the threshold too high, you use your Sketch less, so you lose accuracy. If the threshold is too low, you use Sketch too much, and you use it also for the estimations which you cannot make accurate. So you lose stability and robustness. Like when we start to think like, okay, where the threshold should be, like your first natural idea, okay, it should depend on the size of the stream which you put in the Sketch, because this is how it works for Bloom filters. right? We all know that statistical analysis for Bloom filters, like given the size of the data, that's how big your Bloom filter should be in memory to have a guarantees on precision, like on false positive rate. Here's the same thing, but well, you would think it's the same thing, but not exactly, because threshold should not be a function of the data size. Like consider the two streams. The blue stream is very skewed, like very few objects with very high frequencies, and most of objects low frequency. And the red or orange stream is less skewed, so fewer high frequency objects, more objects with like medium frequency and lower frequency. They have like both streams have the same size, but the sketch is going to be hugely more accurate for the blue stream, like stream A, than B. And the reason for that is simple, because more unique objects in the stream means more hash collisions when you add data to the stream, and the hash collisions are the reasons you get inaccurate results from the sketch. So what we did to deal with this is we coupled the sketch with the count distinct estimator. Like, you know, those count distinct estimators, like hyperlog is the most famous algorithm. It just counts the number of distinct objects in the stream. So when we run the data stream through the sketch, we don't just build the sketch. We also see how many unique objects are in this sketch. We don't use hyperlog. We use a beautiful little algorithm, which was only published last year. It's called like algorithm for the textbook, and it's that simple. I was able to implement like 15 minutes, and which is great. And it actually helps quite a bit. So it tells us how many, like it tells us something about how skewed the distribution is. Like probably like if some of you are statisticians, you can make other suggestions how to discover skewed distributions better than just the counting distinct objects. But as a first approximations, it works pretty good. So that's pretty much all I want to say. So I apologize for running a little bit lower. I blame Peter for that. So just to conclude, cardinality estimations will never be perfect. So you have to build the system so you have to architect for that fact. You cannot take really that fact as an afterthought. So that, because it does have pretty substantial implications for your query optimizer that it cannot rely on cardinality estimation 100% of the time. And so when you're building the query optimizer, you basically have multiple choices, but the main choices here, I think, is like invest more into the pre-execution cost analysis of the query and through data understanding, like figuring out the implicit schema, how the data, the correlation, stuff like that. And then you're going to have great query plans most of the time and some bad query plans some of the time. And this is traditionally how Stardog has been designed over the years. And the second approach is to invest more in the adaptive execution at runtime. So basically embrace the fact that the cardinality estimations are bad. So you get the query plan, which may not be optimal. There might be disasters in there. So let's start executing and then see if we can undo some of the query optimization mistakes at runtime, and changing join order is difficult. But the systems can like change the join algorithms. They can swap left and right hand side of a hash join, for example, stuff like that. So recently, for example, I was sitting through a Snowflake talk, and one of the striking things which I heard was basically the tech lead said, we decided to go for two. Like we decided to precompute less and adapt more because robustness is key. Well, it's a design choice. So that's all I want to say. Yeah, finish with a quote. In Stardog, at least, most bad query plans are due to bad cardinality estimations. True story. All right.
Alrighty. Thanks, Pavel.
Thanks.